Hello, this is Mrs. Sargent, and this is lesson 2.1, the history of the atomic theory. In this lesson, we are going to discuss some different people that have made contributions to the atomic theory, most of them being scientists. And then we're also going to look at the models that they have developed for what they think the atom looks like. So before we get started with that, we need to discuss some vocabulary. The first is a hypothesis. A hypothesis is a possible explanation for your observations. Remember when we did that observing changes lab, we said that observations are based on your senses. So what you see, what you hear, what you feel, what you taste, and what you smell. A theory is a broad, extensively tested explanation of why experiments give certain results, but they can never be proved. You're probably familiar with the Big Bang Theory, the theory of evolution, to name a few. Some other theories that you may have heard mentioned before are string theory and the theory of relativity. Those are all theories. A law is a statement that summarizes results of an experiment or experiments, but does not attempt to explain it. So it's just saying that I know every time I drop a pen, it's always going to fall to the ground because of the law of gravity. I'm not saying why, I'm just saying that this is what happens. And that gravitational constant for here on Earth is that it happens at 9.8 meters per second squared. Now, gravity on the moon is different, but here on Earth, that gravitational constant is 9.8 times 10 to 9.8 meters per second squared. So the first person that made contributions to our atomic theory is Democritus. And Democritus, he was a philosopher. And philosophers, they think, and then they talk about what they think about. And so that's what Democritus did. He said that he thought all matter is composed of atoms, but that was the smallest part of matter. So he would be eating a piece of cheese. Well, I think that these are made of cheese atoms. He'd look at a piece of wood and he'd say, well, this is made of wood atoms. So that's what he thought was the smallest part of matter. The problem with this is that there is no scientific experimentation to back it up. John Dalton, he made his contributions to the atomic theory from 1803 to 1807. And there are 4 parts to Dalton's atomic theory. The first thing that he said is that each element is composed of extremely small particles called atoms. So we have an atom of oxygen and an atom of nitrogen. The second part of his theory is that he said that all atoms of a given element are identical, but the atoms of one element are different from atoms of other elements. So all of our oxygen atoms look the same, all of our nitrogen atoms look the same, but they look different than the oxygen atoms. The third part of Dalton's atomic theory is that atoms from one element cannot be changed into atoms of another element. So hydrogen atoms are always going to be hydrogen atoms. We cannot change them into oxygen atoms. Also, atoms are neither created or destroyed. From this part of his theory, we developed the law of conservation of mass, which says that the total mass before and after a chemical reaction are equal. So if you start the experiment with 10 grams of matter, you should end with 10 grams of matter. And the fourth part of his atomic theory is that compounds are formed when atoms of more than one element combine. The given compound always has the same relative number and kind of atom. From that, we developed the law of multiple proportions, which says that elements combine to form compounds in small whole number ratios. So let's go back up here. Compounds are formed when atoms of more than one element combined. If you remember from that classifying matter activity, we were looking at shapes that have that were representing our atoms. And so if you had a square and a circle that were chemically bonded together, this was a compound. But when we had two squares that were chemically bonded together, this was an element because they are the same type of atom. So a given compound always has the same relative number and kind of atom. The chemical formula for water is H2O, so there's always going to be two hydrogens bonded to one oxygen. So there's a joke. The two guys walked into a bar. The first guy asked for a glass of H2O, and the second said, "I'll have a glass of H2O too." Well, H2O2 is a different compound than H2O. And so the first guy drank his water. The second guy drank some hydrogen peroxide. And the second guy died. You do not want to drink a bottle of hydrogen peroxide in the same way that you would drink a bottle of water because it will end in your death. Now, you may be familiar with that there is hydrogen peroxide in like a whitening toothpaste or whitening mouthwash or something of that nature. There is a little bit of hydrogen peroxide, but you don't consume that bottle of mouthwash. And even if you did, the amount of hydrogen peroxide in that mouthwash is going to be far less than what would be in a whole bottle of hydrogen peroxide. So a little bit of that we ingest is not harmful, but we don't want to just drink a glass of it, like a glass of water. So, and then the law of multiple proportions, the whole number ratios, this just means we can't have half of an atom, or we can't have anything less than a whole number. So Democritus and Dalton's atomic model is the exact same. It's just a circle and shaded in. They called this atomos. And this is where we get the word atom from. Atomos means indivisible. Just of allegiance. Indivisible means that it cannot be divided. It is uncuttable. The next person that contributed to the atomic theory is J.J. Thomson. And in 1897, he did the cathode ray tube experiment. And so cathode rays are particles given off by atoms traveling from the cathode to the anode. So I have a video to show you what is going on here with the cathode ray tube.
To demonstrate a Crookes tube, cathode ray tube, we need a high voltage power source, such as this one. We need the Crookes tube, which has a metal cathode, metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a Bohr magnet. As we turn on the screen, we notice that the electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream. Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
So what happened is we had that cathode ray coming out, and we had a magnet. The magnets have a north and a south end. The south end is negative, the north end is positive. So the first time the guy was holding the magnet, he was holding the south end next to the ray. And what happened is that it bent away. So what did this mean? Well, this meant that the cathode ray must be negatively charged, since like charges repel each other. And this led to the discovery of the electron. So, J.J. Thomson said, well, I know atoms are electrically neutral, so that negative charge has to equal the positive charge in the atom in order to cancel it out. So Thomson's atomic model is a sphere, and these yellow dots, those are the electrons. And then the rest of it is a positively charged mass. Thomson compared this to an English dessert called plum pudding. So he called it the plum pudding model. It's basically like some cake with some pieces of plum intermixed throughout it. But you know what? I've never had plum pudding. I'm not familiar with it. So I was trying to think about some other examples of what this could be like. And I thought about a chocolate chip cookie. Your chocolate chips are the electrons, and mixed throughout is the cookie dough, and that is the positively charged mass. If you wanted to go along the lines of cake and things mixed in with the cake, you could say funfetti cake. The white cake is a positively charged mass, and those different colors, those come from sprinkles, but we could call those the electrons. So Ernest Rutherford had the gold foil experiment. He was actually Thomson's son. And I have a short video to show you about Rutherford.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So based on Thomson's atomic model, Rutherford expected that the alpha particles that were being shot at the gold foil would pass straight through. So this was his hypothesis. So Ernest Rutherford, he shot the alpha particles at the gold foil. So these lines represent the alpha particles. When you have this drawing, I just added the kind of orangish gold rectangle to show you where the gold foil is. The green dots here with the blue clouds around them, those are the gold atoms. So the first thing that he observed from his experiment is that the most of the alpha particles, they go straight through. A lot of them come through. So from this, to try to explain his observations, he concluded that the atom is mostly empty space. Well, the other thing that he noticed is that some are deflected at wide angles. And from this, he concluded that the particles hit a tiny, dense center that he called the nucleus. And then the third thing that he observed is that some of the alpha particles were deflected at small angles. So from this, he concluded that the alpha particles are positively charged. And since like charges repel each other, the nucleus must contain a positive charge. So Ernest Rutherford discovered the nucleus, not the proton. The charge of the nucleus is positive, but the overall charge of the atom is neutral. So Rutherford's atomic model, what he did to change from Thomson's atomic model is he just said that here in the center, this is our nucleus. Where the positive charge is held. And then somewhere throughout the rest of the atom, these black dots, those represent the electrons. James Chadwick, he discovered the neutron. And this is located in the nucleus. And the neutrons have a neutral charge. So I didn't give you any place to draw a model for Chadwick. All I want you to see is that the protons and neutrons are mixed together here, and those are held within the nucleus. Niels Bohr, he agreed that the protons and neutrons are held in the nucleus. But he said those electrons are held in fixed orbitals. So Bohr's atomic model, you have the nucleus here in the center. And then on the rings around it are the electrons, which are found in the green. So even though this isn't our current atomic model, Bohr models do help us learn about the makeup of an atom. And so we'll talk more about that later on in this unit. Erwin Schrödinger, he is responsible for the current model of the atom. His model is also known as the quantum mechanical model. And so what he said that is different is that electrons' actual location is not known. We only know where they most probably are. So I know I only gave you one box for Schrödinger, but I want you to be familiar with both of these pictures. They're used frequently throughout the textbook and throughout my notes and different things like that. So the quantum mechanical model over here is just a bunch of dots, and they are closer together at the beginning, and then they get farther and farther spread out. So you can just take and spread the electrons out. Remember, they're more dense here in the center, and then as you go farther and farther out, they become less dense. For this other model, the nucleus is still here in the center of the atom. but those electrons are held within these orbitals. And again, we don't know where within the orbital the electron is at, but we just know that it is somewhere within these orbitals. So if you missed class, you missed our field trip to the football stadium for our atomic scale experience. But here's a video that kind of explains some of what we talked about together.
In the center of the atom, you would find the size of a football stadium. So imagine a ball the size of a football stadium. And right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium, with a nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, you would have the density of 1 nucleus. Okay, let's review.
So we went to the football stadium. We looked at the size of the stadium in comparison of a marble. It just kind of talked about what is outside of the nucleus and that sort of thing. So that is all for today's notes. Thanks for stopping by. Have a great day.